This lab we're going to learn about centripetal force. In the class we learn when an object on a rotational motion, there's a force towards the center. We call it centripetal force. Fc is center, towards center, which is equal to mass, in this case stopper, mass of the stopper, and the speed of this v, and the radius of this orbital motion. So if you know the radius and if you know the mass, we can calculate, and if we can calculate velocity, then we can calculate centripetal force. So in this experimental setup, we have a plastic tube and also a string. It's a bright color yellow string, and one side of the string we attach a rubber stopper, and on the opposite side we can attach different masses. We call it hanging mass. We can change the weight of the mass, and on one side of this string we mark like a black, we put up, use a permanent marker, and we make a mark so that we can keep this radius fixed when we spin in it, because we hold in from this tube when we spin this rubber stopper to keep this radius constant or known value, and when we spin in this on a horizontal orbit, we never touch this string. It's always we hold in from this tube, so that this radius is fixed, and the opposite side we have a hanging mass. We have a hanging mass mh, but we know if we have a hanging mass, it has a weight force W, which is m times gravity. So we balance this weight. If you increase this weight by changing the hanging mass, we have to increase this friction centripetal force in order to balance. The idea is keep this radius fixed and keep spinning this rubber stopper, and at the same time we change this hanging mass. Every time when we change the mass, hanging mass, we have to increase the speed of this orbit, but we have to keep the radius constant. So when you increase the speed, which means we are increasing the centripetal force, which balance the weight force, or in other words, hanging mass times gravity, which is weight. So basically Fc is the centripetal force we balance with W, or hanging mass. M hanging mass times G. So centripetal force is stopper, mass of the stopper, V square, speed of the stopper, and the radius. So basically we have these two, and we're going to prove that hanging mass, we always know it's a known mass times gravity, which is 9.8, and mass of the stopper we know, and the radius we keep it a constant value, and therefore we can calculate the velocity. This is the table. So in order to do this, we take like trial 1, trial 2. We calculate how long will it take to spin 10 times, because we take 10 because it's accurate, to increase the accuracy, because it's very hard to start from one point and do one revolution and measure the time. Therefore we take 10 times, we measure 10 times, and then finally we divide by 10, and then we have 5 trials, and we record the time and then divide by 10, and then we take the average of these 5 trials, and therefore you don't have to fill up any of these because we already filled this, and we just gave you this average time for this is the mass of the stopper, this is the hanging mass, and the radius we always going to keep constant, 0.5 meters, and we keep changing the hanging mass. So I'm going to show you only one row how to calculate, and then you can complete the rest of the table and answer the questions. Okay, so we have average time, which is period, and you can calculate the velocity using this equation. Velocity is 2 pi and the radius is 0.5 divided by time average, which is this case 684. So which is equal to 4.59 meters per second. Okay, so meters per second, and then frictional force Fc. Fc is m stopper v square over r. M stopper is 0.023. V square is 4.59 square divided by radius 0.5. If you calculate this, which is equal to 0.97 Newton. So here 0.97. And then tension in the string. So tension in the string is, remember, it's in a circular motion. You have centripetal force, and also on the other hand you have hanging mass, which gives weight, which is the tension on the string. This is the tension. Tension is same as hanging mass if it's so, which is equal to m hanging mass times g. Hanging mass is in this case 0.1 kilograms, and g is gravity 0.98. So oh sorry, 9.8 meters per second square. So you get, so you get to very close, so your frictional force is very similar to 0.97 versus 0.98. Tension on the string is close to. So if you fill up these two columns, you will see these two numbers. If you calculate right, frictional force is very closely matched with the tension, and then you can answer to the remaining